Hello mathematicians, we're now going to have a little look at limits and continuity. So two separate issues, but both of them are important in terms of whether or not we can actually find a derivative. And finding a derivative we know is essentially the same thing as whether or not a tangent can be drawn, although it's a little bit more than that. So we're considering whether or not a curve is actually smooth at a particular point, so there's no doubt about the tangent, and also whether the tangent is actually something with its slope defined. So if we have a vertical tangent, then its slope is undefined. So if the slope of the tangent is undefined, that means that the derivative is undefined. We also actually have to have the curve existing. So the curve must be continuous if it's to be differential. Now a really fancy way of saying that is this here, which means that if we consider a point A on a curve, then as we come closer to A from the negative side of A, what's the limiting value of f of A? And as we come closer to A from the positive side of A, what's the limiting value of what is effectively f of A? And do all of those things actually equal the value of the curve at A? So it's just saying that basically if a point on a curve exists, then whether you come from the left or the right, you've got to get to that same spot. If that's not the case, then the curve is not continuous. There's some sort of a break in the curve or a discontinuity, and therefore we can't differentiate it. So it's a very vague concept, the continuity, and there are no calculations as such to do on it. It's just getting your head around the shape of the curve more than anything. So let's think about these examples here. So for the first one, we know that this curve is the hyperbola. We know that the curve doesn't exist at the y-axis and the x-axis, but it's really the y-axis that we're, the x-axis that we're most concerned with. So there is a break in the curve. So it's not continuous at x equals 0. It shoots off to infinity, but there's no y value, there's no f of x when x equals 0. And we know all of that. But what it means is that if the curve doesn't exist at x equals 0, then we can't differentiate it. So it's at x equals 0, it's non-differentiable. For this one here, f of x equals mod of x, or absolute value of x, we know that the curve looks like this, and there's a sharp point. So if there's that sharp point, while the curve is continuous, then where is the tangent? So is the tangent, and I'll just change pen color, the tangent lined up with this curve at the point, or is it lined up with this branch of the curve at the point? So if there's indecision about where the tangent actually is, then that means that the function is not differentiable. Now our next function is a piecewise function, so I'll just sketch that up. So for this piecewise function, the first thing to notice is that as we plot 4 minus x squared, the concave down parabola, for values of x greater than or equal to 0, so on the y-axis the value will actually be 4. And we plot 4 plus x for x less than 0, so that's a straight line with a slope of 1, y-intercept of plus 4. Then this curve is continuous. We come up here as we put values of x in that get closer and closer to 0. This one tends closer and closer to 4, and this one tends closer and closer to 4. So by this definition, the curve is continuous. However, we have some conjecture about what the slope of this curve is. So is it the slope of that straight line there? Is it the slope of the turning point of the tangent there? So again, like this one over here, while the curve is continuous, it's not differentiable at that point because we don't know the tangent. Now, the concept of limits we've come across several times before, and we're just adding a little tool to our arsenal to work with in terms of limits here. So if we wanted to find what happens, say, to this curve, the curve x over x squared plus x, as x headed closer to 0, we know that in theory all that we would have to do is to put 0 in place of x and see what we get. But of course when we do that, this curve is undefined. So if we're going to find what happens as we tend towards 0 for this curve, we just have to do a little bit of algebraic trickery first. So we have limit as x tends to 0 of x, and on the bottom, if we take out x as a common factor, we've got x outside of x plus 1. And in that case, these x's will cancel out, so we want the limit as x tends to 0 of 1 over x plus 1. And at this point, it's fine for us to put x equals 0 in here, because when that becomes 0, our bottom line is 1. So after having taken the limit, it's equal to 1. So as we head towards 0 on this curve, the value we head towards is 1. Likewise, with this curve here, if we plugged x equals 1 into the denominator, we'd be dividing by 0. So first of all, we do the same sort of algebraic simplification that we did in using the h plus 1 or h tending towards 0 methods. So x minus 1 cancels out. We want the limit then as x tends towards 1 of x plus 1, which is going to be 2. So have a go at these. Remember, continuity is sort of, you have to do a bit of blah blah, so you need some words around it. Limits, more of a straight calculation after a little bit of algebraic manipulation.